We want to now look at circular motion, and what we need to be able to do in circular motion is be able to do a few things like this. Define angular velocity, which is just a point moving around another fixed point. And then we want to deduce the angular velocity from that and give the angular acceleration. We also want to find the instantaneous velocity of particle moving around a circle, and but such that it has an angular velocity of omega, and the angular velocities are omega, and it's moving with that speed. So we want to prove the tangential and normal components of the force acting on a particle can be written in these two. So we've got to prove that, and then write down the formula appropriate for the moving around a circle with uniform angular velocity. And that's going to be important. There's uniform angular velocity. So we'll talk about that in a moment, and then solve some problems with that. So what are we talking about? We've got a point and it's moving around in a circle. So at any point time there, we could describe, instead of in terms of its Cartesian equation, we can determine its position in terms of its radius and the angle there that it's creating from a line here. Now, the rate at which that angle changes is what we call the angular velocity. So what we're going to call omega here. So the angular velocity is the rate of change of the angle over time. So we measure that in radians per second. So that's important too when we get to some problems. So our omega there could be written as the theta dt there, or we could write omega as a theta dot. So that's what we're talking about. Rate of change of the angle over time is what we're going to call our angular velocity and give it the letter omega. So therefore the angular acceleration is the rate of change of the angular velocity. So theta double dot, or d omega dt, or d dt of d omega dt, or d squared omega theta on dt squared, or we could write it as omega dot. So any of those are talking about the angular acceleration, so rate of change of the angular velocity. So what we want to do is calculate the velocity of p. So we want to consider two things: the components along the x-axis and the y-axis. So if we go back to our diagram, so along the x-axis, what would it be? And on the y-axis, what would it be? We're going to get r cos theta, and for y is r sin theta. And we've done lots of that sort of work before, because cos theta would be x on r, and sin theta would be y on r from that diagram. Now, if we want to find the rate of change of the position of x, but we're in terms of theta, we're going to have to apply the chain rule. So that's where this comes about. So we derive r cos theta, r is a constant, and theta will change. So we get r cos theta differentiates to sine theta, but we multiply by the theta dt as well. So that's because it's a chain rule, because technically x is going to be in, and we're going to have an expression for theta there, so we need to multiply by the theta dt. But that becomes our angular velocity. That's omega. So we can write it as a minus omega r sine theta. And we do the same thing for y. We apply the derivative with respect to t, so we apply the chain rule. So we get r cos theta and the theta to t, which is omega. So therefore our velocity then would be omega times r. So we can look at our velocity there overall would be, and we can draw this up, would be the absolute value of the omega dot by omega dot, which you could do when you're looking at the distance there. You apply Pythagoras on that, and you're going to get omega r. So that's what we're looking at there. And you can also look at, well, what direction is it going? So we get y dot over x dot there be minus 1 on tan theta, which basically means OP is perpendicular to the direction of v. So what does that mean for us there? The velocity of the particle is tangential to the circle. And that makes sense, because if you're spinning something around, it's going to be tangential to that circle, and it has a magnitude of omega times r. So it's moving at that speed, omega times r, and it's going to be tangential. So you basically, if you're you got a ball on a string, and you keep moving it around, if you let it go at any stage, the ball's going to fly off in a straight line. It's going to move, and that straight line would be the tangent. It's not going to keep curling around. As soon as you let go of the ball, or the string breaks, the ball goes flying, in a straight line away from the circle and on the tangent line to that circle. So acceleration here. Again, we end up with our positions, and we got our velocity in terms of x and y. So we do the same thing for our acceleration. So again, we're going to differentiate with respect to t of this equation here, and when we do that, we're going to end up using the product rule, because we've got omega, which is the theta to t. So we're going to have to differentiate with a function there. We can take the r out because that's a constant, but we get the omega to t times sine theta, and then the derivative of the function there with the cos, and then derivative of cos, so we get the omega times cos theta. Sine theta goes to minus cos, so that's why it becomes positive, and the theta to t. So which we can bring down to omega dot if we want to write it in that terms, and omega squared, because that would be omega again. So all I've done is apply the product rule on that using those two functions. To get for the acceleration in terms of y, we do the same. We've got two functions there. Our r comes out the front because that's a constant. And so we derive omega with respect to t, leave cos theta, leave omega, and derive cos theta with respect to t, which would be d theta to t. Remember, omega is the theta to t already, so that's why it's just getting the second derivative there, or the derivative of the angular velocity. So when we look at that, if we're looking at force, remember force is mass times acceleration, so that's where we start to get this expression, because we just multiply mass times that expression and mass times that expression there to get our forces that are happening. And what do we mean by our forces that are happening? Well, basically, we're going to have forces in terms of x, we're going to have forces in terms of y. But what we want is to resolve those forces in terms of the normal and tangential forces. So we really don't care too much for what's happening for the forces in terms of x and y. We want to know what forces are happening on the tangent and in the normal to the tangent there. So what we've done here, we draw a little diagram up, and I've played around with it here. This would be the forces along the tangent, and these are the forces along the normal. So notice this would be even though it's up here, that would be the same as the forces in the normal there. This would be, if I'm going to draw up this diagram, I'm looking at the diagram here, and this would be minus the force on the tangent, because it's going in that direction. So that's why it gets a negative there. So we get that angle being theta, because that's going to be a corresponding angle, and that's 90 degrees, and that's 90 degrees, so that would be theta as well. So from that, I'm able to get these expressions and get start to resolve the forces for the normal and the tangent in terms of the forces for y and x. So we're using this diagram here. We get sine theta is the force of the normal over the force of the y component. So, and then I'm able to get Fn equals Fy sine theta. And similarly for this one, cos theta here would be function of the normal force over the function over the forces in x. So that's where we're able to get that one and get Fn is equal to Fx cos theta. And then because they're both Fn, well, that's the sum of the forces there. Remember, the forces that are acting here would be the sum of the forces that are acting this way and this way. So that's where we're starting to get the idea of our forces for the normal being combined there, and they're going to be proportional in terms of whatever a theta is there. So we are able to multiply those out, and using the fx that we had in the previous slide, so the f of x there, the forces on x and the forces on y, we're going to use and multiply them out. We get this expression, and then we start getting, nice thing happening is that these two cancel, and we can get the minus, we can take the minus m r omega squared out, and we're left with a bracket with cos squared theta plus sine squared theta, which is 1, which leaves us with minus m omega squared r. So that's the forces that are happening on the normal there, m omega squared r. So we can also start to look at that in terms of the tangential forces. So ft here, I use cos theta, and over ft is on fy. So we can write ft as fy cos theta. And for the tangential forces this time, I've got to consider this direction this time for sine of theta, because it's going to be going this way, and because of that, because of the function of x, the forces in x are moving that direction. So that's why I get a minus forces of the t over the forces of x, or f of t would be minus forces of x sine theta. So that's where it becomes a minus there, plus the fy cos theta. So these two are summed because they're both acting for the forces in t. And again, we multiply them out and collect our terms. And again, we get these ones going to cancel. And we can collect these terms out the front and get sine squared theta plus cos squared theta, which gives m times r times omega dot, or the acceleration there. So what does that mean for us? Well, if we start to look at the idea, remember we wanted to have a look at the idea, it moves at a uniform speed, so a constant speed, which means that if it moves at a uniform speed, then our angular acceleration is 0. If that's the case, that the forces on the tangent start to become 0. So if it's a constant velocity, there's nothing happening with the acceleration in terms of the angle. So the forces on the tangent become 0, which means that only force that's going to occur is going to be directed towards the center. So, and it has a constant magnitude of mass times acceleration. So mass times acceleration would equal minus m omega squared r, which leaves us with the acceleration then being omega squared r. So that's what we're going to get. There's acceleration is going to be this constant value as well. We can play around with that in all our equations to get accelerations also v squared on r. So we can use either in terms of we can find acceleration in terms of velocity, or we can find acceleration in terms of the angular velocity. So it depends on what the question asks and what we need. So there's all our equations that we need to start off with in circular motion. Go through the algebra, find out how we do. We should be able to prove that those situations exist every time. So be careful as you go through and make sure you understand how we get down to these two situations.